Hello, and welcome to Quiet Learning for Sleep. This is your peaceful space to unwind, to let go of the day, and to drift into deep, restful sleep while learning softly about our universe. Here, we take gentle journeys through calm ideas, stories from science and nature, space and time, history and life, all whispered at a soft pace, without rush, without noise, and without pressure. You do not need to focus or remember anything. This is learning the quiet way, where your mind floats and drifts and rests, while curiosity stays softly awake in the background. If you'd like, before you get comfortable, you can subscribe and gently like this video. Doing it now means you won't forget later, and it helps others like you find this calm, sleepy corner of the world. Now, allow your breath to slow just a little. Let your shoulders relax. Let your thoughts soften, like clouds drifting across a calm evening sky. There is nowhere you need to go, nothing you need to do, and nothing expected from you here. This time belongs to rest, comfort, and gentle curiosity. And if you drift to sleep along the way, that is not only allowed, it is welcome. So settle in, let yourself melt into stillness, and allow your mind to float quietly as we begin. In the earliest decades of the space age, when humanity first began reaching beyond Earth, Venus occupied a special and uncertain place in the human imagination. It was bright, close, and familiar in the night sky, yet almost completely unknown in reality. Unlike the Moon, whose surface could be mapped with telescopes, or Mars, whose seasonal changes invited speculation, Venus hid itself behind an unbroken veil of cloud. What lay beneath that veil was not merely a scientific question, but a profound mystery that shaped early planetary science and space exploration. For astronomers observing from Earth, Venus was frustratingly opaque. Its thick cloud cover reflected nearly all visible light, revealing nothing of the surface below. Even powerful telescopes showed only a smooth, featureless disk. This made Venus fundamentally different from other nearby worlds. Where Mars teased observers with polar caps and dark markings, Venus offered no clues at all. The planet's proximity suggested importance, but its concealment demanded exploration rather than observation. Before spacecraft, scientists relied on indirect measurements and educated guesses. Venus was similar in size and mass to Earth, leading many to believe it might also be similar in nature. Some theories imagined shallow oceans beneath the clouds, warmed by constant sunlight. Others proposed dense jungles or vast swamps, shaped by a humid and slow-rotating climate. These ideas were not fantasies in the popular sense. They were serious hypotheses grounded in limited data and the assumption that Earth-like planets might follow Earth-like evolutionary paths. At the same time, there were warning signs. Venus was closer to the Sun than Earth, receiving significantly more solar energy. Its atmosphere, though poorly understood, appeared thick. Radio observations hinted at high surface temperatures, but the data was ambiguous. Some scientists suggested that the heat came from the upper atmosphere rather than the surface. Others argued that the readings were exaggerated by atmospheric effects. There was no consensus, only uncertainty layered upon uncertainty. This lack of clarity made Venus scientifically irresistible. If Venus was Earth-like, it could represent an alternative evolutionary outcome for a rocky planet. If it was hostile, it could serve as a cautionary example of how planetary climates can diverge catastrophically. Either result would be valuable. Venus mattered not because it promised comfort or familiarity, but because it offered contrast, a chance to test assumptions about planetary habitability itself. The geopolitical context amplified this scientific curiosity. During the Cold War, space exploration was inseparable from national prestige. The Soviet Union and the United States both sought firsts. First satellite, first human, first probe to another world. Venus, being closer than Mars and energetically easier to reach, became an attractive target for demonstrating technological capability. Reaching Venus meant mastering interplanetary navigation, deep space communication, and autonomous spacecraft operation far beyond Earth orbit. For the Soviet space program in particular, Venus presented both an opportunity and a challenge. Early Soviet planetary missions favored bold objectives, often accepting high risk in exchange for potential breakthroughs. Venus fit this philosophy well. It was nearby enough to attempt repeatedly, yet unknown enough that even partial success could yield groundbreaking data. A probe that failed halfway down the atmosphere could still return information no one had ever measured before. Another reason Venus mattered was psychological. The planet had long been associated with Earth in both myth and science. Often called Earth's sister planet, Venus forced scientists to confront the possibility that similarity in size and composition does not guarantee similarity in outcome. Understanding Venus meant understanding Earth's uniqueness or fragility. In this sense, Venus was never just about Venus. It was about learning where Earth fits within a broader spectrum of planetary possibilities. From an engineering perspective, Venus represented an extreme test environment. Even before precise measurements, scientists suspected that conditions would be challenging. Designing spacecraft that could survive unknown pressures, unknown temperatures, and unknown chemical environments required innovation. Every assumption had to be questioned. Materials, electronics, structural design, all had to account for scenarios far beyond those encountered in Earth orbit or lunar missions. This uncertainty forced a different mindset. Unlike missions designed to explore familiar environments incrementally, Venus missions demanded resilience against the unexpected. Probes had to be prepared to fail gracefully, returning whatever data they could before being overwhelmed. Success was not defined by longevity, but by endurance. Surviving minutes could be as valuable as surviving days, if those minutes occurred in an environment never before sampled directly. Venus also mattered because it challenged optimism. In the early space age, there was a quiet expectation that nearby planets might be hospitable, or at least approachable. Venus tested this belief more harshly than any other world. Each probe sent toward it carried not only instruments, but expectations that would be reshaped repeatedly as data returned from deeper and deeper layers of the atmosphere. The decision to focus so heavily on Venus reflected a willingness to confront uncomfortable truths. If Venus turned out to be uninhabitable, it would suggest that planetary environments can diverge dramatically even when starting from similar conditions. This realization would later influence thinking about climate, atmospheric stability, and the long-term future of Earth itself. Venus mattered because it was a reminder that nature does not guarantee balance. As missions accumulated, Venus gradually transformed from a blank disk into a defined, if hostile, world. But at the beginning of the Venera program, none of this was known. Venus was a question mark, bright, nearby, and stubbornly silent. Sending machines into that silence was an act of curiosity, ambition, and quiet bravery, undertaken without certainty of reward. In choosing Venus, the Soviet scientists and engineers were not simply racing for a destination. They were choosing a problem, a planet that refused to explain itself from afar. Venus mattered because it demanded direct engagement. It could not be understood from a distance. It had to be entered layer by layer, at great cost, and with great patience. This chapter marks the beginning of that engagement. Before landers, before images, before proof of crushing pressure and extreme heat, there was only a bright planet in the sky, and a decision to approach it anyway. Venus mattered because humanity chose to ask what lay beneath the clouds, even when the answer might be inhospitable, final, and irreversible. Before the first Venera probes ever left Earth, Venus existed more as a theoretical object than a physical place. Scientists had equations, models, and indirect measurements, but no direct experience. The planet's thick cloud cover blocked visible light completely, turning Venus into a blank canvas onto which human imagination and scientific inference were projected. Unlike Mars, whose surface features could be sketched and debated, Venus resisted interpretation, forcing researchers to rely on radio signals, spectroscopy, and assumptions rooted in Earth-based analogies. One of the strongest assumptions came from similarity. Venus and Earth are nearly the same size, have comparable mass, and are both rocky worlds located relatively close to one another in the inner solar system. This resemblance suggested a shared origin, and possibly a shared early history. Many scientists reasoned that if Earth developed oceans, an atmosphere, and eventually life, Venus might have followed a similar path, perhaps diverging only slightly due to its closer proximity to the Sun. These ideas were not naive. They were grounded in the limited planetary science of the time, and in the absence of contradictory evidence. Because Venus rotates slowly and is perpetually covered by clouds, some models suggested a globally warm but stable climate. The clouds were imagined as water vapor, trapping heat gently and spreading it evenly across the planet's surface. In this view, Venus might host shallow seas or swamp-like environments, warmed by constant sunlight and moderated by atmospheric circulation. The slow rotation was thought to prevent extreme temperature differences, creating a world that, while exotic, was still potentially habitable in some form. At the same time, other scientists were uneasy with these optimistic interpretations. Radio observations detected unusually strong microwave emissions from Venus, which implied very high temperatures. The challenge was determining where those temperatures originated. Some argued that the heat came from the upper atmosphere, heated by the sun, and re-radiating energy downward in a way that exaggerated surface estimates. Others suggested that the readings reflected genuine surface conditions, hinting at a runaway greenhouse effect long before the term became common. The data could support multiple interpretations, and debates persisted without resolution. The uncertainty was compounded by ignorance of Venus's atmospheric composition. Spectroscopic measurements showed carbon dioxide, but the proportions were unclear. Water vapor was suspected, but not confirmed in meaningful quantities. Without knowing the atmospheric makeup, scientists could not reliably model pressure, temperature, or chemical behavior near the surface. Venus's atmosphere could be thin or crushing, humid or dry, reactive or inert. Every scenario remained plausible because none could be tested directly from Earth. This ambiguity made Venus uniquely compelling. It was not merely another planet to visit, but a problem to solve. Each unanswered question amplified the value of even the smallest piece of direct data. A single temperature reading, a single pressure measurement, or a brief transmission during atmospheric descent could overturn decades of speculation. Venus was unknown, not because it was distant, but because it was hidden, and that concealment made it one of the most scientifically valuable targets in the solar system. For the Soviet space program, this uncertainty aligned well with the strategy of incremental risk. Rather than waiting for perfect knowledge, engineers and scientists accepted that early missions might fail, provided they failed informatively. A probe destroyed high in the atmosphere could still measure density and composition. A transmitter that survived only minutes could still confirm or refute entire classes of theories. The unknown planet did not demand perfection, it demanded persistence. As planning progressed, Venus began to shift in scientific perception. It was no longer viewed primarily as a potential second Earth, but as a test case for planetary extremes. Could a rocky planet evolve into something radically different from Earth, despite similar beginnings? Could atmospheric feedback loops drive a world into permanent instability? These questions mattered far beyond Venus itself. They touched on fundamental principles of climate, planetary evolution, and long-term habitability. The lack of direct knowledge also forced humility. Venus reminded scientists that observation from afar has limits, and that nature does not conform to expectation simply because it appears familiar. The planet became a symbol of scientific restraint, a reminder that theories must eventually confront reality, even when that reality is hostile to instruments and assumptions alike. Venus could not be understood by analogy alone. It required direct contact, however brief. By the time the first Venera probes were prepared, Venus was no longer imagined as a welcoming world waiting to be discovered. It was imagined as a question, possibly benign, possibly lethal, but certainly decisive. The unknown planet mattered because it represented the boundary between speculation and evidence. Crossing that boundary meant sending machines into conditions no one could fully predict, trusting that whatever they transmitted before falling silent would permanently change humanity's understanding of nearby worlds. This chapter closes at the edge of that uncertainty. Venus remained hidden, unresolved, and resistant to clarity. Yet the decision had already been made to approach it anyway. The unknown planet was about to stop being unknown, not all at once, but layer by layer, transmission by transmission, as the Venera missions began their long process of revealing a world that would turn out to be far more extreme than anyone had imagined. When the Soviet Union began sending spacecraft toward Venus, failure was not an unexpected outcome. It was an assumed part of the process. The technology required to reach another planet, navigate autonomously through deep space, and survive entry into an unknown atmosphere was still in its infancy. Each mission carried uncertainty, not as a side effect, but as a defining feature. The early Venera probes were not designed with confidence. They were designed with questions. The first attempts to reach Venus faced challenges almost immediately after launch. Rockets failed, guidance systems malfunctioned, and communication links were lost before probes ever left Earth orbit. In some cases, spacecraft were successfully launched, but never achieved the correct trajectory. In others, signals vanished silently, leaving engineers to reconstruct events from fragments of telemetry. These early failures rarely produced dramatic conclusions. Instead, they produced silence, ambiguity, and long periods of analysis. Unlike later missions, these failures were not publicly dissected in detail. Much of the early Soviet space program operated under strict secrecy. Missions that failed were often not announced at all, or were described vaguely. Yet internally, each failure became a source of technical knowledge. Engineers examined vibration profiles, thermal behavior, signal strength, and timing discrepancies. Even when a probe never reached Venus, it still taught lessons about launch dynamics, deep space communication, and system resilience. As missions progressed, some probes began to approach Venus successfully, only to fail during atmospheric entry. At this stage, the planet began to reveal its hostility incrementally. Signals returned during descent indicated rapidly increasing pressure and temperature. Transmissions cut off sooner than expected, sometimes abruptly, sometimes gradually. Each cutoff point marked a boundary, an altitude beyond which survival was no longer possible for that generation of hardware. These partial descents were not disappointments. They were revelations. Each second of transmission during atmospheric entry provided data that reshaped engineering assumptions. The atmosphere was denser than expected. The pressure increased faster than models predicted. Temperatures rose relentlessly, not leveling off as some theories had suggested. Venus was not merely warm, it was overwhelming. One of the most important lessons from these early failures was that Venus could not be approached incrementally, in the same way as Mars or the Moon. On those worlds, gradual improvements in landing systems could extend mission duration. On Venus, the environment imposed hard limits. Electronics failed not because they were poorly designed, but because the ambient conditions exceeded their fundamental operating ranges. This realization forced a complete redesign philosophy. Another lesson was psychological, as much as technical. Engineers learned to redefine success. A probe that transmitted data for a few minutes before failing was not a failure. It was a success constrained by physics. This shift in mindset allowed the Venera program to continue, rather than collapse under unrealistic expectations. Surviving briefly on Venus became an achievement rather than an embarrassment. Repeated failures also revealed patterns. Certain systems failed consistently under heat stress. Certain materials deformed or degraded faster than anticipated. parachutes behaved unpredictably in dense atmospheric conditions. Each repetition refined understanding. Failure stopped being random and became instructive. Over time, engineers learned not just what failed, but why it failed, and under what conditions. Communication itself became a fragile victory. The dense atmosphere interfered with radio transmission, absorbing and scattering signals. Maintaining a stable link during descent required precise antenna orientation and transmission power. Early probes struggled to maintain contact, not because transmitters were weak, but because the environment actively worked against signal propagation. This forced improvements in modulation techniques and transmission strategies. These early missions also revealed a deeper truth about Venus. It did not allow compromise. Unlike environments where partial protection could yield partial survival, Venus demanded absolute solutions. Either a system could withstand extreme pressure and heat, or it could not function at all. There was no middle ground. This realization pushed Soviet engineers toward radical solutions rather than incremental ones. The accumulation of failures gradually transformed Venus from an abstract unknown into a defined adversary. Each failed probe added detail to the portrait. Venus was hot, dense, chemically aggressive, and mechanically unforgiving. It destroyed probes not violently, but inevitably. Understanding this inevitability was crucial. It allowed designers to stop hoping for mercy and start designing for confrontation. Over time, the Venera program developed a rhythm: launch, silence, partial data, failure, analysis, redesign. This cycle repeated again and again, not hurriedly, but methodically. The absence of immediate success did not signal futility. It signaled progress unfolding at the only pace the problem allowed. These early failures are often overlooked because they did not produce images or long-lasting landers. Yet without them, nothing that followed would have been possible. They stripped away illusions, narrowed uncertainties, and established the physical reality of Venus with uncompromising clarity. The planet was not ambiguous anymore. It was deadly in specific, measurable ways. By the end of this phase, Venus was no longer unknown. It was known to be extreme, known to be hostile, known to demand specialized engineering beyond anything attempted before. The early failures did not delay success. They defined it. They transformed the Venera program from exploration by hope into exploration by endurance. This chapter closes not with triumph, but with clarity. The Soviet engineers now understood that reaching Venus was not a matter of navigation alone. It was a matter of survival under conditions that exceeded earthly experience. The lessons learned from failure were not optional. They were the foundation upon which every later Venera success would be built, layer by layer, failure by failure, until survival itself became possible. As the Venera probes began descending into the atmosphere of Venus, the planet revealed itself not through images or landscapes, but through measurements that changed steadily with altitude. Temperature readings, pressure values, and chemical signals arrived slowly, line by line, each one representing a layer of atmosphere that no human instrument had ever entered before. These measurements were often brief, sometimes lasting only minutes, yet their implications were profound. Each data point forced scientists to revise not just models of Venus, but assumptions about planetary climates as a whole. At higher altitudes, the atmosphere appeared deceptively manageable. Pressure increased gradually, and temperatures, though elevated, remained within ranges that electronics could tolerate for short periods. But as the probes continued downward, the atmosphere thickened dramatically. Unlike Earth's atmosphere, which becomes progressively thinner with altitude and remains relatively gentle near the surface, Venus's atmosphere grows denser at a relentless pace. Instruments recorded pressure, climbing faster than predicted, revealing an environment that compressed structures and systems long before reaching the ground. On Earth, atmospheric pressure at sea level is about 1 bar, a value so familiar that it often goes unnoticed. Early expectations for Venus ranged from a few bars to perhaps 10 or 20. What Venera discovered was an atmosphere approaching 90 bars at the surface. This is equivalent to the pressure experienced nearly 1 kilometer beneath Earth's oceans. Such pressure is not merely uncomfortable or dangerous, it is mechanically destructive. Metals deform, seals fail, and structural weaknesses are exposed instantly. For a spacecraft, surviving this environment requires an entirely different category of engineering. Temperature measurements followed an equally unforgiving trajectory. As probes descended, temperatures did not plateau or fluctuate. They rose steadily and predictably, climbing beyond the boiling point of water and continuing upward without interruption. By the time later Venera landers reached the surface, temperatures were measured at approximately 460 degrees Celsius. This heat was not transient or localized. It was a stable, omnipresent condition, maintained by the planet's atmospheric structure and energy balance. The source of this extreme heat became clear through chemical analysis. Venus's atmosphere is composed almost entirely of carbon dioxide, with small amounts of nitrogen and trace gases. Carbon dioxide is highly effective at trapping infrared radiation, preventing heat from escaping into space. On Venus, this greenhouse effect operates without moderation. Solar energy enters the atmosphere, warms the surface, and becomes trapped beneath thick layers of gas, reinforcing heat rather than dissipating it. Over geological time, this process intensified, locking Venus into a permanent thermal state far beyond Earth's experience. Above the lower atmosphere, Venera probes detected extensive cloud layers composed primarily of sulfuric acid droplets. These clouds reflect much of the sunlight, which explains Venus's brilliance in the night sky. However, reflection alone does not guarantee cooling. The clouds interact with radiation in complex ways, allowing visible light to scatter while trapping infrared heat below. The result is a system that looks bright and temperate from afar, but maintains lethal conditions beneath. Atmospheric density added another layer of complexity. Near the surface, Venus's atmosphere behaves less like a gas and more like a dense fluid. Descent through this environment is slow, not because of safety, but because drag forces are immense. Parachutes behave differently, compressing and heating under stress. Falling through Venus's atmosphere can take over an hour, during which conditions worsen continuously. The slow descent offers no relief. It merely extends exposure to rising temperature and pressure. Wind measurements further challenged expectations. At cloud level, Venus's atmosphere exhibits superrotation, circling the planet far faster than the planet itself rotates. Winds reach hundreds of kilometers per hour, transporting clouds around the globe in a matter of days. Near the surface, however, winds slow dramatically despite the dense atmosphere. This contrast revealed a planetary circulation system unlike anything on Earth, driven by thermal gradients rather than surface features or rotation speed. Chemical sensors detected a dynamic and reactive environment. Sulfur compounds, carbon monoxide, and trace gases participated in cycles influenced by sunlight and extreme heat. These reactions helped stabilize the atmosphere over long timescales, preventing collapse or escape. Venus was not in a temporary state of imbalance. It had reached a stable, if catastrophic, equilibrium, one that resisted change and persisted for billions of years. For engineers, these findings transformed mission design. Electronics could not simply be shielded. They had to be isolated inside thick pressure vessels, often spherical to distribute stress evenly. Insulation layers slowed heat transfer, but could not stop it. Cooling systems were designed not for comfort, but for delay, buying minutes of operation before internal temperatures exceeded survivable limits. Every second of surface operation became a victory against thermodynamics. Each Venera descent refined this understanding. When instruments failed at specific temperatures or pressures, those failures became measurements themselves. A transmitter shutting down at a known temperature established a boundary. Structural deformation marked pressure thresholds. Venus's atmosphere was mapped not just through success, but through controlled loss. Destruction became data. These discoveries reshaped planetary science. Venus demonstrated that Earth-like size does not guarantee Earth-like outcomes. It showed that atmospheric composition and feedback mechanisms can push a planet into an irreversible state. This realization would later influence climate science, exoplanet studies, and long-term models of planetary evolution. Venus became a reference point, not for habitability, but for instability. By the end of this phase of exploration, Venus was no longer a mystery hidden behind clouds. It was a measured environment with defined limits, known gradients, and predictable lethality. The deadly atmosphere was no longer theoretical. It had been entered, sampled, and endured, briefly, by machines designed specifically to confront it. This chapter closes with a shift in perspective. Venus was not hostile in a chaotic sense. It was hostile in an orderly, consistent, and scientifically understandable way. That understanding made survival possible, at least for moments. And those moments would soon become longer, as engineers applied what they had learned to the next generation of Venera landers, preparing to face the surface itself. Designing a machine to survive on the surface of Venus required abandoning nearly every assumption that engineers had learned from Earth-based aerospace engineering. Venus is not merely hotter or denser than Earth. It operates in a regime where familiar materials, familiar electronics, and familiar safety margins cease to function. The challenge was not to make something comfortable or efficient, but to make something that could resist inevitability for a short time. On Venus, survival is temporary by definition, and engineering is about delaying failure rather than preventing it. The most immediate problem was pressure. At Venus's surface, atmospheric pressure reaches approximately 90 times that of Earth. This pressure acts uniformly in all directions, compressing structures continuously. On Earth, aircraft and spacecraft are designed to hold pressure inside while facing vacuum outside. On Venus, the situation is reversed. The lander must resist pressure from the outside, not by sealing gently, but by refusing to deform. Any weakness in shape or joint alignment becomes a point of collapse. To address this, Venera landers adopted a spherical pressure vessel design. A sphere distributes stress evenly, minimizing concentrated loads that could cause cracks or buckling. This choice was not aesthetic. It was mathematical. Flat surfaces bend under pressure. Cylinders deform unevenly. A sphere resists collapse because every point supports every other point. The pressure vessel became the heart of the lander, dictating nearly all other design decisions. Material selection followed the same logic of resistance. Lightweight alloys common in spacecraft were insufficient. Engineers turned to thick titanium and steel, accepting mass penalties because mass was no longer the enemy. On Venus, mass provided strength, and strength provided time. The landers were intentionally heavy, compact, and dense, built not to fly gracefully, but to sit and endure. Temperature posed an even greater challenge. At approximately 460 degrees Celsius, Venus's surface is hot enough to melt lead and soften many structural metals. Electronics fail far earlier. Semiconductors lose function. Insulation degrades. Lubricants evaporate. Unlike pressure, which can be resisted structurally, heat must be managed dynamically. Yet active cooling systems require energy, and energy on Venus was severely limited. The Venera solution was thermal inertia. Instead of attempting to cool continuously, engineers designed the landers to heat up slowly. Thick insulation layers surrounded the pressure vessel, creating a thermal barrier that delayed the flow of heat inward. The internal volume was kept small to reduce exposed surface area. Components were arranged compactly to minimize thermal gradients. The goal was not to stay cool, but to stay cooler than the outside for just long enough to transmit data. Electronics were chosen and modified specifically for high temperature tolerance. Where possible, components were simplified. Redundancy was introduced not to increase performance, but to increase survival probability. Circuits were designed to tolerate drift in electrical properties as temperature rose. Calibration was expected to degrade. Accuracy would suffer. Function, however, was prioritized over precision. Power systems also reflected this philosophy. Venera landers relied on batteries rather than solar panels, because sunlight at the surface is weak and diffuse beneath thick clouds. Batteries were insulated alongside electronics, their chemical stability carefully tested under extreme heat. Energy budgets were calculated not for hours or days, but for minutes. Every watt consumed shortened operational life, so instruments were sequenced carefully, activated only when needed. Descent engineering added another layer of complexity. Venus's dense atmosphere produces enormous drag, slowing descent, but also generating heat. Parachutes deployed at high altitude had to survive acidic clouds and high temperatures while maintaining predictable behavior. Materials were chosen for chemical resistance rather than flexibility. As probes descended deeper, parachutes were often discarded intentionally to allow controlled free fall through denser layers. reducing exposure time. Landing itself was not gentle in the terrestrial sense. Venus's surface conditions meant that shock absorbers had to function under extreme heat and pressure simultaneously. Mechanical systems were simplified wherever possible. Fewer moving parts meant fewer failure points. The lander did not need to move or adjust. It needed to arrive upright and intact. Once on the surface, the environment attacked relentlessly. Heat penetrated insulation. Pressure stressed every seal. Chemical reactions began immediately. Engineers expected gradual system degradation, and they planned accordingly. Instruments were prioritized. Cameras transmitted first. Environmental sensors followed. Every second of operation was scheduled in advance, because improvisation was impossible once the lander touched down. Communication systems face their own challenges. Venus's dense atmosphere absorbs radio waves, particularly at certain frequencies. Transmitters had to be powerful enough to overcome this attenuation while operating within limited power budgets. Antennas had to remain functional despite thermal expansion and chemical exposure. Maintaining a stable signal was itself a triumph of engineering under constraint. Perhaps the most remarkable aspect of Venera engineering was its acceptance of loss. Engineers did not aim for indefinite survival. They aimed for meaningful survival. A lander that operated for 5 minutes was a success. 10 minutes was exceptional. Longer durations represented triumph over physics, not mere technical achievement. This mindset allowed designers to make trade-offs that would be unacceptable in other missions, focusing everything on immediate data return. Over successive missions, survival time increased gradually. Insulation improved. Materials were refined. Electronics were hardened further. Each additional minute on the surface represented years of accumulated engineering knowledge. Progress was slow, but it was real. Venus did not yield easily, but it yielded predictably, allowing human ingenuity to inch forward against overwhelming conditions. Engineering for Venus reshaped how scientists thought about exploration. It demonstrated that extreme environments do not require perfection, only persistence. Machines can be built not to conquer, but to endure briefly and report honestly. Venera landers were not elegant. They were resolute. They did not adapt to Venus. They resisted it. This chapter ends with a simple truth. Venus forced engineers to confront the limits of materials, electronics, and time itself. Every Venera lander was a compromise between strength and duration, knowledge and survival. And with each compromise refined, humanity moved closer to achieving something unprecedented, not just reaching another planet, but standing upon it, however briefly, and learning directly from the most hostile surface ever explored. The first successful landings of Soviet spacecraft on the surface of Venus did not feel like triumph in the conventional sense. There were no celebrations, no dramatic confirmations, and no immediate certainty that the mission had succeeded. Instead, there was cautious listening, patient decoding, and a growing realization that something unprecedented was happening. A machine built on Earth had entered the atmosphere of another planet, survived a descent, and was still transmitting from the surface. Even if only briefly, humanity had arrived somewhere entirely new. A Venus landing begins long before contact with the surface. As the probe separates from its carrier spacecraft and enters the upper atmosphere, it encounters resistance almost immediately. Unlike Mars, where the atmosphere is thin and forgiving, Venus's atmosphere grips the descending probe early, slowing it dramatically while heating its exterior. Temperatures rise steadily, not in bursts, but in a continuous climb. Pressure follows, increasing with depth in a way that cannot be stopped or mitigated once descent has begun. The descent phase unfolds slowly. Parachutes deploy high above the surface, where temperatures are already extreme, and clouds of sulfuric acid surround the probe. These parachutes are not designed for comfort or elegance. They exist to manage time, to slow the probe enough for instruments to sample atmospheric layers, and to reduce impact forces later. As the probe descends further, the atmosphere becomes so dense that parachutes become liabilities, increasing exposure to heat. At this point, parachutes are jettisoned deliberately, allowing the probe to fall faster through the final layers. During this descent, instruments transmit continuously. Pressure sensors record values climbing steadily. Temperature sensors register relentless heat. Chemical analyzers sample atmospheric composition. Wind sensors infer motion through changes in descent behavior. Each measurement is time-stamped, each transmission precious. Engineers know that failure is approaching. The question is not whether the probe will stop transmitting, but how much it will transmit before it does. As the surface approaches, the probe's structure bears increasing stress. External temperatures exceed the limits of exposed materials. Heat begins to penetrate insulation layers. Inside the pressure vessel, electronics warm gradually, approaching thresholds beyond which functionality degrades. Yet systems continue to operate, not because conditions are safe, but because time has not yet run out. The moment of landing itself is not dramatic. There is no dust plume visible to cameras, no bounce or roll captured in motion. The probe simply stops descending. Shock absorbers compress. Mechanical stress spikes briefly, then settles. The lander rests on the surface of Venus, upright if all has gone well, surrounded by an atmosphere dense enough to press against every surface continuously. At this point, a new phase begins. The probe is no longer moving through layers. It is immersed in a constant environment of extreme pressure and heat. Temperature outside remains around 460 degrees Celsius. Pressure remains near 90 bars. Nothing fluctuates significantly. Venus is stable in its hostility. The probe is now racing not against changing conditions, but against time itself. Immediately after landing, the lander begins its surface operations sequence. This sequence is not interactive. There is no waiting for instructions from Earth. Light travel time makes real-time control impossible. Every action has been planned in advance, ordered by priority. Cameras activate first. If images are to be transmitted, they must be sent before heat disables imaging systems, or electronics drift out of specification. The first images from Venus's surface were among the most extraordinary achievements of planetary exploration. They did not show alien landscapes in the dramatic sense. They showed rocks, soil, shadows, and a flat horizon beneath a dense sky. Yet these images carried weight far beyond their content. They were proof that a machine had seen another planet from its surface and survived long enough to report what it saw. After imaging, other instruments activate in sequence. Temperature sensors confirm surface heat directly. Pressure sensors verify atmospheric density at ground level. Chemical analyzers sample the immediate environment. In later missions, microphones even recorded sound. The wind moving through a dense atmosphere, slow and heavy compared to Earth's breezes. Inside the lander, conditions deteriorate steadily. Despite insulation, heat penetrates the pressure vessel. Internal temperatures rise minute by minute. Electronics drift. Voltages change. Systems begin to fail, not catastrophically, but progressively. One instrument stops responding. Another returns erratic data. Communication weakens as transmitters overheat. Each additional minute of operation is a victory. Engineers monitor telemetry, watching values climb toward known failure points. They do not intervene. They cannot. The mission is unfolding exactly as designed. The lander is not expected to survive indefinitely. It is expected to endure long enough. Some Venera landers survived for mere minutes. Others, refined through years of engineering improvement, survived longer, tens of minutes, then over an hour. Each increase in survival time represented an enormous achievement. On Venus, extending operational life by even a few minutes required overcoming fundamental physical limits. The significance of these landings cannot be overstated. Before Venera, no spacecraft had soft landed on another planet. The moon had been visited, but it lacks atmosphere and extreme conditions. Venus represented a different class of challenge entirely. These landings proved that controlled descent, impact survival, and surface operation were possible even under the most hostile planetary conditions known. Scientifically, the surface data confirmed long-suspected truths and revealed new ones. The ground was solid, not molten. Rocks appeared angular and weathered, shaped by chemical processes rather than erosion by water. The lighting was diffuse, filtered through thick clouds. Visibility was limited, but sufficient to map the immediate surroundings. Emotionally, though rarely expressed openly at the time, these missions represented quiet triumphs. There were no astronauts involved, no flags planted, no public ceremonies. Yet a machine had reached a place humans could never survive, and had spoken briefly before falling silent. That achievement required patience, restraint, and acceptance of limits, qualities rarely associated with space exploration, yet essential here. As each lander eventually failed, the mission did not end in disappointment. Failure was expected. The silence that followed was not defeat, but completion. The probe had done what it was built to do. It had endured long enough to turn speculation into measurement and imagination into reality. This chapter closes with that moment of stillness, the lander resting on Venus's surface, surrounded by crushing pressure and unbearable heat, transmitting steadily until physics reasserts itself. In those minutes of operation, humanity achieved something quietly monumental. Not just reaching another planet, but standing upon it, however briefly, and learning directly from the most unforgiving surface ever explored. When the Venera landers finally came to rest on the surface of Venus, they entered an environment that had no true equivalent anywhere else explored by humanity. The surface was not dramatic in motion or change. It did not erupt, quake, or swirl violently. Instead, it existed in a state of near perfect stability, defined by extremes that never relented. Heat, pressure, and chemical aggression were constant, unchanging, and absolute. Venus did not attack suddenly. It pressed inward, continuously, from every direction. The temperature at the surface of Venus remains close to 460 degrees Celsius at all times. This heat does not vary meaningfully between day and night, equator or pole. Venus rotates so slowly, and its atmosphere redistributes heat so efficiently, that the concept of weather as experienced on Earth simply does not apply. There are no cool mornings, no warm afternoons, no seasonal relief. Every moment is the same moment, repeated endlessly. Heat is not an event on Venus. It is the baseline state of existence. At these temperatures, many familiar materials behave differently. Metals soften, chemical bonds weaken, electrical resistance changes. Components that rely on precise tolerances begin to drift outside their functional range. Even solid rock on Venus is affected. Surface minerals undergo slow chemical alteration, not through water erosion, but through reactions with atmospheric gases. The ground is dry, rigid, and chemically active all at once. Pressure adds another layer of strangeness. At approximately 90 bars, Venus's atmosphere exerts the same force as nearly a kilometer of ocean pressing down from above. This pressure is not felt as weight, but as compression. Every exposed surface is pushed inward continuously. Gaps close. Seals tighten. Any cavity becomes a liability unless perfectly reinforced. The atmosphere itself behaves less like a gas and more like a thick, invisible fluid surrounding everything. Despite this density, movement near the surface is minimal. Winds are slow, often measured in just a few meters per second. This creates an eerie contrast, an atmosphere heavy enough to crush, yet calm enough to feel still. The air does not roar, it presses. Sound travels efficiently through this dense medium, but little motion exists to generate it. Venus's surface is not noisy. It is oppressive in its quiet. Lighting on Venus is dim and diffuse. Thick clouds scatter sunlight before it reaches the ground, eliminating sharp shadows and directional glare. The sky appears yellow-orange, illuminated evenly from all directions. Objects cast soft, indistinct shadows, if any at all. Visibility is limited, not by darkness, but by atmospheric scattering. Distance fades gradually rather than abruptly. The horizon exists, but it feels closer than it should. Images returned by the Venera landers show a landscape that appears almost familiar at first glance. Rocks lie scattered across flat terrain. The ground looks solid and stable. There is no lava flow in motion, no dramatic terrain features in the immediate vicinity. And yet nothing in these images is truly familiar. The colors are muted. The textures suggest chemical alteration rather than erosion. The stillness feels unnatural. Chemical measurements reveal why. Venus's atmosphere near the surface is rich in carbon dioxide, with traces of sulfur compounds and other reactive gases. These chemicals interact continuously with surface materials. Rocks weather not through wind or water, but through slow chemical corrosion. Over geological time, this process reshapes the surface without carving it. The result is a planet that looks ancient and unchanged, yet is constantly reacting at a molecular level. The absence of liquid water is perhaps the most defining characteristic. Water is a powerful agent of change on Earth. It erodes, dissolves, transports, and transforms. On Venus, water cannot exist as a liquid. Any water that once existed evaporated long ago, contributing to the runaway greenhouse effect that now defines the planet. Without water, landscapes evolve differently. Sharp edges persist. Fine dust behaves differently. Geological processes slow and simplify. Time itself feels different on Venus. The planet's slow rotation means a single day lasts longer than an Earth year. Yet because temperature remains constant, this long day produces no thermal rhythm. Sunrise and sunset are subtle transitions rather than dramatic events. The surface experiences no daily cooling or heating cycle. It simply remains hot, always. For the Venera landers, this environment offered no forgiveness. There was no period of relative safety, no moment when conditions eased. From the instant of landing, the clock was ticking steadily toward failure. Heat soaked inward. Pressure remained constant. Chemical exposure continued unabated. The lander existed inside a countdown, defined by physics rather than malfunction. And yet, within this hostile stillness, meaningful science occurred. Instruments measured surface composition. Cameras transmitted images line by line. Sensors confirmed atmospheric behavior, predicted only by models before. Each data point carried enormous significance, precisely because it was gathered where no human could ever stand. Venus's surface taught scientists that a planet does not need chaos to be hostile. Stability itself can be deadly. A perfectly balanced greenhouse atmosphere can trap a world in permanent extremes. Geological calm does not imply habitability. Familiar size does not guarantee familiar outcomes. This chapter ends with an image not of destruction, but of endurance. A small, heavily armored machine rests silently on an alien surface, surrounded by heat and pressure beyond human tolerance. It does not move. It does not adapt. It simply exists for as long as it can, recording, transmitting, and confirming what Venus truly is. Not a sister to Earth, but a cautionary world shaped by relentless equilibrium. When the Venera landers finally fell silent on the surface of Venus, their missions did not end in failure or disappointment. Silence was not a surprise. It was not even a setback. It was the expected conclusion of a carefully planned encounter with an environment that no machine could endure indefinitely. On Venus, success was never measured by longevity. It was measured by whether meaningful information could be gathered before physics inevitably reclaimed control. Each lander's final moments followed a similar pattern. Telemetry grew unstable as internal temperatures rose. Signal strength weakened as electronic components drifted beyond their designed operating ranges. Individual instruments ceased responding, one by one, not abruptly, but gradually. Engineers watching from Earth understood exactly what was happening. They had modeled these failures years earlier. Every lost channel was anticipated. Every minute gained was a bonus. In conventional space missions, longevity is often synonymous with achievement. Satellites are praised for surviving decades in orbit. Rovers are celebrated when they exceed their expected operational lifetimes. Venus demanded a different mindset entirely. Here, endurance was measured in minutes, not years. A lander that survived for half an hour had already achieved something extraordinary. One that lasted longer had pushed against the absolute limits of materials and electronics. The silence that followed each mission was therefore not emptiness, but closure. Data streams stopped not because the mission had failed, but because it had completed its purpose. Venus had been measured directly. Its atmosphere had been sampled from top to bottom. Its surface had been touched, photographed, and analyzed. No further transmission could add fundamentally new information without an entirely new class of technology. From a scientific perspective, the results were transformative. Venera confirmed that Venus's extreme surface conditions were not localized or temporary. They were global, stable, and long-lived. The planet was not experiencing a transient greenhouse phase. It was locked into one. This realization reshaped theories of planetary climate evolution and forced scientists to reconsider how easily Earth-like planets could diverge into uninhabitable states. Venus became a benchmark, not for life, but for climate catastrophe. Its thick carbon dioxide atmosphere demonstrated the full power of the greenhouse effect when left unchecked. Models of early Venus suggested that the planet may once have possessed oceans, possibly even conditions favorable to life. Venera's measurements showed how completely and permanently those conditions had vanished. Water was gone, hydrogen lost to space, oxygen consumed by surface reactions. This understanding extended far beyond Venus itself. It influenced how scientists interpreted exoplanet data decades later. When astronomers began detecting planets around other stars, Venus served as a reminder that size and location alone are insufficient indicators of habitability. A planet can reside in a star's so-called habitable zone and still be utterly hostile, depending on atmospheric composition and feedback mechanisms. Technologically, Venera represented a masterclass in constraint-driven engineering. The landers were not elegant. They were dense, compact, and brutally pragmatic. Every design decision was shaped by inevitability. Insulation did not stop heat. It delayed it. Pressure vessels did not eliminate stress. They distributed it. Electronics did not resist temperature indefinitely. They tolerated it briefly. This philosophy, designing for graceful failure rather than impossible perfection, would later influence missions to other extreme environments. The psychological dimension of these missions is often overlooked. Unlike human spaceflight, Venera unfolded quietly, largely without public spectacle. There were no astronauts to interview, no live broadcasts, no dramatic visuals, until data was decoded and reconstructed. The achievements were technical, patient, and understated, and yet, in many ways, they were more audacious than crude missions closer to home. Landing on Venus required trusting calculations completely. Once a probe entered the atmosphere, there was no correction, no rescue, no adaptation. Everything that would happen had already been decided. Engineers could only wait, listen, and interpret. This required a rare form of confidence, not optimism, but acceptance. Acceptance that failure was built into the mission, and that success existed within narrow, unforgiving margins. The images returned from Venus's surface carried a strange emotional weight. They were not beautiful in the conventional sense. They showed rocks, soil, and an empty horizon beneath a dense sky. but they were images of a place that had resisted observation for centuries, a place hidden behind clouds, speculation, and myth. Seeing Venus as it truly is dissolved illusions and replaced them with knowledge. As decades passed, no subsequent mission returned to Venus's surface with the same determination. Orbiters continued to study the planet from above. Radar mapped its terrain. Spectrometers analyzed its atmosphere remotely, yet the surface itself remained largely untouched. The reason was not lack of interest, but respect. Venus had revealed its nature clearly. Returning would require new technology, new materials, and new ideas. In this sense, Venera did not merely explore Venus. It set a boundary. It defined what was possible with 20th century engineering, and where those possibilities ended. That boundary became a reference point for future mission planners. When scientists discussed returning to Venus, they did so with humility, aware of the lessons written into every failed component and every minute of survival gained. The silence of the Venera landers still echoes through planetary science. It is a reminder that exploration does not always mean persistence. Sometimes it means brief contact, followed by understanding. Venus does not invite long visits. It offers clarity quickly, and then withdraws it just as quickly. The Venera missions accepted this bargain, and emerged victorious because of it. This chapter closes not with loss, but with recognition. Recognition that success can be measured in moments, that knowledge can be extracted from extreme environments without conquest, and that even the most hostile worlds can teach us something essential about ourselves and our fragile home. Venus spoke briefly through Venera, and what it said continues to shape how we explore the universe. Venus did not merely answer scientific questions, it reframed them. Once the Venera missions confirmed the planet's true surface conditions, Venus could no longer be discussed as an incomplete mystery or an unrealized Earth-like world. It became something far more unsettling and far more valuable, a complete example of how a planet can change irreversibly, not through catastrophe, but through stability. Venus is not broken. It is functioning exactly as its physical laws allow, and that is precisely what makes it dangerous as a comparison. For much of human history, Venus occupied a special place in imagination. It appeared bright and inviting in the sky, often described as Earth's sister planet, due to its similar size, mass, and composition. Before space exploration, many assumed that beneath its clouds might lie oceans, forests, or at least temperate conditions. These assumptions were not unreasonable. Venus and Earth formed from similar materials, at similar distances from the Sun, during the same era of planetary formation. If Earth could support life, why not Venus? The answer, revealed slowly and decisively by Venera, lies in feedback loops. On Earth, climate systems contain stabilizing mechanisms. Liquid water absorbs heat, evaporates, condenses, and redistributes energy. Plate tectonics recycle carbon dioxide between the atmosphere and the interior, preventing runaway accumulation. Biological processes further regulate atmospheric composition. These systems do not guarantee safety, but they provide resistance against extremes. Venus lacks these stabilizers. Once early, Venus began to warm. Water evaporated into the atmosphere. Water vapor itself is a powerful greenhouse gas, trapping additional heat and accelerating warming. As temperatures rose further, oceans could not recondense. Ultraviolet radiation from the sun broke water molecules apart in the upper atmosphere. Hydrogen escaped into space. Oxygen reacted with surface materials. The loss of water was permanent. Carbon dioxide then accumulated unchecked. Without oceans to absorb it, and without tectonics to recycle it efficiently, carbon dioxide built up until it dominated the atmosphere. The greenhouse effect intensified until Venus reached a thermal equilibrium far hotter than Earth could ever naturally experience. And once that equilibrium was reached, it locked itself in place. Venus did not oscillate. It stabilized at catastrophe. Venera's measurements confirmed every step of this process. Surface temperatures were uniform across the planet. Atmospheric composition showed overwhelming carbon dioxide dominance. Pressure values matched models of long-term accumulation rather than transient events. Venus was not in the middle of becoming uninhabitable. It had completed that transformation billions of years ago. This realization changed how scientists think about planets everywhere. It showed that habitability is not a permanent trait. It is a temporary phase. A planet may pass through conditions favorable to life, and then exit them forever. Venus may have once resembled Earth more closely than Mars ever did, yet today, it is far more hostile. The lesson extends beyond Venus. When astronomers observe exoplanets orbiting distant stars, they often rely on indirect measurements: mass, radius, orbital distance. Venus teaches that these parameters are insufficient. Two planets can appear nearly identical in size and location, and yet diverge completely due to atmospheric evolution. Without understanding composition and feedback mechanisms, appearances are misleading. Venus also reframes discussions about climate change on Earth. While Earth is not Venus, and human activity cannot reproduce Venusian conditions directly, the underlying physics is shared. Greenhouse gases trap heat. Feedback loops amplify changes. Stability can shift. Venus represents an extreme end of a continuum, not an alien exception. It is a reminder of what planetary systems are capable of when balance is lost. The Venera missions forced scientists to confront uncomfortable continuity rather than comforting separation. Venus is not hostile because it is different. It is hostile because it followed physical rules faithfully. The same equations govern Earth's climate, only operating within a narrower range. This does not imply inevitability, but it demands respect for limits. There is also a philosophical dimension to Venus that Venera brought into focus. Humanity often frames exploration as expansion, conquest, or endurance. Venus rejects those narratives. It cannot be colonized. It cannot be terraformed with foreseeable technology. It does not invite settlement. Instead, it invites observation, humility, and learning. It offers knowledge without accommodation. In this sense, Venus is not a destination, but a demonstration. It demonstrates the consequences of atmospheric imbalance. It demonstrates the limits of engineering. It demonstrates how planets remember their histories long after surface features fade. Every measurement returned by Venera reinforced the idea that planets are processes, not static objects. The silence that followed the Venera lander's final transmissions symbolized more than technical failure. It symbolized completion. Venus had spoken clearly. Further repetition would yield diminishing returns without revolutionary advances in materials and cooling. Exploration paused, not because curiosity ended, but because understanding had reached a natural boundary. That boundary continues to shape future missions. When modern spacecraft observe Venus from orbit, they do so with the weight of Venera's lessons behind them. They know what lies below. They know the cost of contact. Any future return to the surface will not repeat the past. It will require fundamentally new approaches, perhaps using high-temperature electronics, or entirely different mission architectures. Venus also occupies a unique emotional space in planetary science. It is familiar, yet inaccessible, close, yet unreachable, bright in the sky, yet hostile beyond imagination. The Venera missions stripped away romanticism and replaced it with clarity. That clarity is not discouraging. It is grounding. As this chapter draws to a close, Venus stands not as a failure or a tragedy, but as a completed story. A planet that formed, evolved, transformed, and stabilized into a state utterly incompatible with life. A planet that teaches by example rather than invitation. A planet that reminds us that Earth's gentleness is neither universal nor guaranteed. In the quiet stillness of Venus's surface, beneath crushing pressure and eternal heat, lies one of the most important lessons in planetary science: that survival is not the default condition of worlds. It is a fleeting alignment of circumstances, and understanding that alignment may be humanity's most valuable discovery of all. Long after the last Venera lander stopped transmitting, the surface of Venus did not change its behavior in response. Venus does not pause, cool down, or soften when a mission ends. It continues to hold the same temperature, the same pressure, and the same chemical atmosphere, hour after hour, year after year. The landers became silent not because Venus won in a dramatic way, but because the environment is steady and uncompromising, and the landers were designed to last only a little while within it. In a strange way, that steadiness is the most haunting feature of Venus. There is no storm you can wait out, no night you can endure until morning arrives, no seasonal relief that makes survival feel possible. On Earth, we think of ruins as places shaped by water, wind, oxygen, and biology. A metal object left outdoors rusts, paint peels, plastics crack, and plants grow through gaps. On Venus, many of those familiar processes either do not exist or happen very differently. There is almost no free oxygen in the lower atmosphere, so classic red rusting is limited. There is no liquid water to dissolve, transport, and erode. There are no roots seeking cracks, no microbes forming biofilms, no insects pulling fibers apart. And yet Venus is not gentle. Its destruction is slower and steadier, driven not by rain and life, but by heat, pressure, and hot chemistry that never stops. Start with the simplest question. Are the Venera landers still there? In the broad physical sense, yes. The landers did not evaporate. They did not sink into an ocean. They did not disintegrate instantly into dust. Most likely, their main structural bodies remain on the surface as inert objects, like small artificial boulders resting among natural rocks. Their shapes may be slightly altered, their outer layers chemically changed, their exposed parts dulled and darkened. But Venus is not a world that quickly rearranges its surface on human timescales. A Venera lander would not be swept away by a river, swallowed by soil saturated with water, or buried rapidly by plants and debris. It would simply remain where it fell, slowly becoming less distinct. But still there does not mean still intact, and it certainly does not mean still functional. The moment a Venera lander stopped transmitting, it became a sealed container, filled with increasingly hot internal air and gradually failing materials. Heat continued to soak inward until the entire structure approached the ambient temperature of Venus. Batteries overheated and degraded. Solder joints softened and then re-solidified in slightly changed shapes. Wires expanded and relaxed. Insulators aged. Mechanical stresses redistributed. There is a quiet inevitability to this. Once power and communication stop, the lander is no longer an active system, and the only remaining processes are physical ones, governed by time. One of the most important ideas for understanding Venus hardware is that temperature is not just high, but continuously high. On Earth, even in harsh deserts, there is a night. Materials cool, and cooling relieves stress. On Venus, there is no meaningful cooling cycle at the surface. The day-night temperature difference near the ground is small because the atmosphere is dense and excellent at transporting heat. That changes how materials fail. Instead of cracking from repeated hot-cold cycles, many components are pushed towards slow deformation, chemical drift, and long-term structural creep. Venus is a planet where time itself becomes an engineering force. Creep is the word engineers use for slow deformation under constant stress, and it becomes important at high temperature. Many materials that appear solid and strong at room temperature will, at around 460 degrees Celsius, behave like extremely stiff putty over long periods. Under their own weight and the steady external pressure, brackets can sag, thin plates can bow, and seals can compress further. These changes might be tiny over a month, noticeable over a year, and significant over decades. Creep is especially relevant on Venus because the stress does not go away. Pressure remains. Heat remains. The material is never allowed to rest back into a cool, stable shape. Now consider chemistry. Venus's atmosphere is mostly carbon dioxide, with traces of sulfur compounds and other reactive species. Higher up, clouds contain sulfuric acid droplets. Near the surface, the chemistry is less about acid rain and more about hot gas reactions. At high temperatures, reaction rates increase, and materials that are stable on Earth can become chemically restless. Oxidation can occur through trace oxidizers. Surface coatings can break down. Polymers can char. Some ceramics can change microstructure. Even glass can be affected at the edges where stress and chemistry meet. The planet does not need liquid water to be corrosive. It uses heat as its accelerator. Because Venera landers operated for short periods, we do not have long-duration before and after images of the same hardware after years on Venus. So scientists infer long-term effects from laboratory tests, chemical models, and from the behavior of Venus surface minerals observed by later missions. The point is not a precise corrosion rate down to the millimeter per year. The point is direction. Venus pushes materials toward chemical equilibrium with its atmosphere, and that equilibrium is different from Earth's. Over time, surfaces tend to dull, coatings tend to fail, and exposed metals tend to develop altered layers, that may flake, reform, and settle into a new balance. Pressure adds another steady influence. 90 bars is not just a number, it is a permanent load pressing on every external surface. For the main pressure vessel, a spherical shell distributes this load well, but external parts are more vulnerable. Camera ports, antenna mounts, connector covers, thin brackets, and any protrusion that cannot share load smoothly with the main structure. Under pressure and heat together, slow deformation becomes more likely. Even tiny changes can matter because they change alignments. Alignment matters for optics, for antennas, and for the mechanical stability of anything that sticks out into the atmosphere. Venus does not snap objects quickly, as if by impact. It reshapes them by patience. Then there is the question of dust and burial. Venus has fine surface material, and while winds near the ground are usually slow, the dense atmosphere means even slow winds can push particles with meaningful force. Dust can accumulate in sheltered corners, cavities, and joints. Electrostatic charging may cause particles to cling. Chemical adhesion may help dust stick to hot surfaces. Over decades, a lander could become partially dusted, not quickly like a sandstorm burying a vehicle, but slowly like a film that thickens into a layer. And dust does not need to bury the lander fully to change how it looks. A thin coating can reduce contrast, erase sharp edges, and make an artificial object blend into the landscape. It is also worth remembering that Venus's surface may be geologically active over long timescales. Radar maps show large volcanic plains and features that suggest resurfacing in Venus's history. But recent in geology can mean millions of years. A Venera lander could, in principle, be covered by lava or fractured by tectonic motion, but that would be an accident of location and timing. The typical fate is quieter, a small object aging in place, slowly altered by heat, pressure, and chemistry, while the ground around it remains largely unchanged from one human century to the next. This gives us a useful mental image. The Venera landers are now part of Venus's geology, in the same way a meteorite becomes part of a desert. They are foreign objects, but they are also stable objects. Over time, they heat to ambient temperature, react at their surfaces, collect dust, and become increasingly similar to the background in color and texture. If you could visit centuries from now, you might need to look carefully to see that a particular oddly rounded rock is actually a machine. The lander's shape might still be distinctive, but its surface would no longer look clean or manufactured. It would look like it belongs. From the perspective of biology and contamination, Venus offers a stark contrast to worlds like Mars. On Mars, there is concern that terrestrial microbes might survive, contaminate, and confuse the search for indigenous life. On Venus, at the surface, the environment is so extreme that biological survival is essentially impossible. Heat sterilizes. Chemistry breaks complex organic molecules. Pressure crushes delicate structures. Even if a microbe were shielded briefly, it would not find liquid water, not find mild temperatures, and not find a stable chemical niche. The landers did not seed Venus with life. They carried Earth materials into a place that sterilizes by default. And yet, even without biology, Venus preserves stories. The Venera landers preserve a story of design choices: thick pressure vessels, compact forms, minimal moving parts, cameras that scanned slowly line by line, and instruments prioritized by a strict sequence that assumed inevitable failure. Each lander is a physical record of what humans believed was possible at the time it was built. The landers are artifacts of a particular era, shaped by Soviet industrial capability, by Cold War urgency, and by scientific curiosity that was willing to accept short-lived success. If we zoom out further, the landers also preserve a story about the nature of exploration itself. Many missions aim for longevity. Rovers meant to drive, orbiters meant to map for years, telescopes meant to observe for decades. Venera aimed for contact. It aimed to touch, measure, and confirm. It was exploration by brief encounter. That style of exploration can be underestimated, but it can be extraordinarily powerful. A short measurement in the right environment can change a field of science more than a long mission in the wrong place. Venera showed that minutes of truth can be worth more than years of guessing. There is even a quiet acoustics lesson hidden in Venus's atmosphere. Because the air is dense, sound would travel differently there. Not simply faster in a cartoon way, but differently in how it carries and how it is absorbed. A small vibration might propagate more efficiently through dense gas. The same wind speed can feel heavier because the moving air contains more mass. At the same time, the thick atmosphere can damp certain frequencies and make distant sounds feel close and muffled. If you imagine standing beside one of the landers, you might hear the wind not as a sharp hiss, but as a low, steady presence, as if the planet is breathing slowly. Modern mission planners who discuss returning to Venus's surface often talk about high-temperature electronics, such as devices made from silicon carbide, and about new cooling strategies, such as phase change materials, heat pipes, or even active refrigeration. They also discuss new architectures, landers that can operate for days, balloons that float in the temperate cloud layers, and stations that might survive for weeks. These ideas exist because Venera proved two things. The surface can be reached, and direct measurements matter. The old missions ended quickly, but they opened the door. They changed Venus from an unreachable threat into a solvable engineering challenge, even if the solution is difficult. If a future lander were to search for the old Venera sites, it might use radar, not only from orbit, but potentially from the surface as well. Artificial shapes scatter radar differently than natural rocks. A pressure vessel, a landing ring, or a camera port could create distinctive reflections. A new mission could compare geometry, surface reflectivity, and scattering patterns to look for something manufactured. Finding an old Venera lander would be like finding a time capsule. Not because it would still function, but because it would still exist as evidence of a moment when humans reached Venus directly. For now, though, the Venera landers remain what they have been for a long time: quiet machines resting in perpetual heat. Their antennas do not transmit. Their cameras do not scan. Their sensors do not respond. And yet they remain meaningful. They are physical evidence that a human civilization once built a pathway from Earth to Venus, crossed it, and left objects behind. They are small, dense punctuation marks on a planet that otherwise contains no sign of life, no sign of visitors, and no sign of concern. If you imagine Venus in the deep future, tens of thousands of years from now, the landers will still be traveling through time without traveling through space. They will be slowly altered by chemical equilibrium, perhaps darkened, perhaps dusted, perhaps partially buried, perhaps deformed by creep. Some parts may crack as stresses concentrate. Some seals may fail and allow the atmosphere into internal cavities, accelerating chemical changes from the inside. But the planet will not hurry to erase them in the way Earth would. Without rain and without biology, some kinds of decay are slower, even while heat is relentless. And there is another quieter possibility, that the landers persist for a very long time in recognizable form, not because Venus is gentle, but because Venus is stable. A stable extreme can preserve as well as destroy. When conditions do not cycle, some failure modes slow down. When there is no rain, some erosion stops. When there are no roots, some cracking never begins. Venus trades away the dramatic day-to-day chaos of Earth for a steady pressure cooker of heat and chemistry. In that steadiness, artifacts can remain in place for long stretches of time, gradually becoming more like the planet around them, but not necessarily disappearing quickly. So when we say silent machines on a hostile world, we are not describing abandonment. We are describing a completed act of exploration that continues to exist physically. The landers are monuments of contact rather than settlement. They are reminders that a mission can succeed even if it ends quickly, and that knowledge can be extracted from a place that offers no hospitality. They represent a type of bravery that is quiet, not the bravery of humans stepping onto a surface, but the bravery of building something that can survive long enough to speak, and accepting in advance the moment it will stop. Venus holds these machines without acknowledging them. The atmosphere presses on them, day after day. The heat surrounds them, hour after hour. The chemistry reacts with them, year after year. And still they remain, quiet witnesses to a time when the unknown planet became known, through brief transmissions that crossed interplanetary space and changed how humanity thinks about worlds. And in that quiet persistence, there is a final lesson that fits the spirit of quiet learning for sleep. Exploration is not always loud. Sometimes it is a sequence of careful measurements, followed by long silence. Sometimes the most important achievements are not the ones that continue forever, but the ones that reveal something true and then end, leaving behind both data and artifacts that outlast the moment. The Venera landers ended their lives quickly, but their presence on Venus continues, and their scientific legacy continues with them, like a small human signature pressed gently into a world that does not bend.
you.